अस्सलाम। हमारी इस वीडियो में हमने स्टडी करना है कि इन्वर्टर एक जो हमारा नॉट गेट होता है उसकी स्विचिंग कैरेक्टरिस्टिक्स क्या है। हम बेसिकली ये क्यों स्टडी करना चाहते हैं, द रीज़न बिहाइंड इज़ कि हम अभी तक जो चीज़ें स्टडी कर चुके हैं उसमें हमने ये देखा है कि हाउ कैन वी डिज़ाइन लाइक सिमेट्रिक इन्वर्टर और सिमेट्रिक डिज़ाइन वेयर वी हैव इक्वल डिलेज. That was because like we can control the width and obviously the width of PMOS and NMOS. Now what we want to study is how the frequency is controlled, or what would be the maximum frequency on which our circuit can operate, and what factors limit that maximum frequency. So to study that, we have to study these like inverter switching characteristics. We are considering as a first example, we are considering it as a inverter example because it is an easier circuit. It has only two gates. One is in pull up network and the other one is in pull down network. So we have to study we will study this characteristics. So the first video session is about the introduction of these inverter characteristics, inverter switching characteristics. So what we know is like the speed of a circuit is measured usually by the time delay between like input and out and corresponding output. Like the speed of a circuit, what we know is कि ये जो स्पीड है बेसिकली ऑफ अ सर्किट इज इट डिपेंड्स ऑन इनपुट एंड द कॉरेस्पॉन्डिंग आउटपुट. हाउ इट डिपेंड्स इज कि हमारी जब भी इनपुट चेंज होगी like we have to measure our output after some delay, and that delay basically measures the speed of our circuit. Like this is our switching speed of our circuit. Designing of fast CMOS circuits is both like challenging and obviously it is also critical. So we have to deal with both these factors. What we know is our output reacts to an input, but obviously that output cannot change suddenly. Like it has some delay, it changes slowly. We have studied that earlier as well. Like it changes over time. We cannot change it in square wave fashion. So we can say that this delay is measured in rise time or fall time, like using rise time and fall time. Like one is the our rise time, output rise time, when our output rises from 0 to high voltage, and the other one is our fall time, that basically when output our output changes from high voltage to low voltage. This can be represented somewhat like this. Here we have an inverter shown. like हमारे पास यहाँ पे एक इनपुट है, इनपुट वोल्टेज है, और हमारे पास correspondingly एक आउटपुट वोल्टेज आएगी. This input voltage is a square wave like shown it here, and our output voltage is the behavior of our output is somewhat like this. We have some fall time, which basically is the delay between our input from high to low voltage, and the other is our fall time, rise time, which is basically the delay when our output changes from 0 to VDD volts. So we have two different times, which are rise time and fall time, which represents our outputs with some delays. And we also know that the resistance offered by NMOS and PMOS, obviously in driving the output, these formulas can be used for our resistances. Like if we have to find the resistances for NMOS, we use this formula where we have beta N, and then we have PMOS resistance of PMOS where we use beta P. And similarly, output of our inverter can be seen as a capacitor. Like for example, we have this inverter here, we have our input and output terminals, but we know that there are some parasitic capacitances present on within this inverter, at this output junction, like at this junction where we have drains of PMOS and drains of NMOS, we have this parasitic capacitance. This capacitance is known as CDP. Like this is our drain parasitic capacitance. And similarly, we have this capacitance that is like CDN, that is NMOS drain parasitic capacitance. So we can say that the output at our output, like this output point, we have two capacitances. One is like our CDN and the other one is our CDP. We have seen these formulas here when we calculated our these parasitic capacitances. So we can say that this like parasitic capacitance, the CDN and CDP, both depend on like this factor, which is our like Wn. If we increase Wn, the width of our like PMOS or NMOS, we will increase the parasitic capacitance, and obviously that will affect our rise time and fall time. We will see that how it depends on rise time and fall time calculations. And in a logic network, like we have seen there is an example of this logic network where this NOT gate is driving like this 3 NOT gates. So like in these like NOT gates, we say that every logic gate drives other gates. Like obviously here in this example, a single NOT gate is driving three NOT gates. But there could be some other examples where our like NOT gate could be driving our like AND gate or OR gate or whatever could be the requirement. So the number of gates driven in is fan out of the circuit. Like fan out is basically it basically tells us how many gates are driven in a circuit. Like we have 3 gates which are driven here. So it means like the fan out of the circuit is 3, and the fan out acts as a load to the driving circuit. Like this fan out is basically acts as a C load. Like you can see that this point is driving these 3 like NOT gates. So we can say that this CL, this load capacitance, adds to this the capacitance of the output capacitance of this NOT gate. So we can say that like if we consider this point here, like this example here, Cin in this example is CGP plus CGN. Like here we have CGP and CGN. So this is total input capacitance. While if we like see this output, like this output of our NOT gate is driving here 3 different like inverters. So we can say that the load capacitance, the CL capacitance is equal to 3CN because we are driving 3 circuits here, 3 input, like 3 inverters here. So the input capacitance of each gate is summed up together to get the total load capacitance. And we can also say that each inverter will drive like this inverter. For example, this inverter is driving the total output capacitance of this inverter would be CMOS plus CL. This CMOS is obviously given by CDN plus CDP. That is like the output capacitance here at this PMOS and at this NMOS. So the total output capacitance is CMOS plus CL. And this allows us, like this will allow us to calculate rise and fall times. Like this output capacitance basically allows us how we can calculate the rise and fall times together. So to understand it better, or like to understand these capacitances which occur at the output and input of a gate circuit, like at input of an inverter, we have to like solve an example. So now we will solve an example to understand these capacitances and how they could be how they could be affecting our like rise time and fall time.
So हमें क्या करना है कि
एक एग्जांपल हम स्टडी कर लेते हैं कि हाउ डू वी अप्लाई दिस एनालिसिस ऑफ these capacitances on an example of an inverter. So what we do is we will let us apply this analysis on an इन्वर्टर. सो हम बेसिकली जो कैपेसिटेंसेस का एनालिसिस है वो हम अप्लाई करते हैं अभी एक इन्वर्टर की एग्जांपल पे. सो हमारे पास जो इन्वर्टर डिज़ाइन है वो है बेसिकली, उसकी हम डायग्राम यहाँ पे ड्रॉ कर लेते हैं. लाइक वी हैव वन, दिस वन इज और P plus area and this one is all NMOS area. Then we have like polymaterial here, and we also connect like this region here with VDD and this region here with ground, and these two are connected together. Like if I extend this to here. And one more thing is, like we have studied earlier कि जहाँ पे हमारे पास when there is a like higher width of our MOSFET, we use multiple like contacts. So here we are using 4 contacts in this example, and also on this side as well. And we are using 2 contacts here, similarly here as well. I'm just like drawing it not correct. So we also have like this point as an out. And what other features we have for this like inverter design? Like this point is VD. We have here our output, and then we have here our Vin, that is our input, and this size of PMOS is 8 micrometer, and size of this NMOS is 4 micrometer. And what else we have is like this width from here to here is 2 micrometer, and there are other different parameters which we need to like have for our PMOS, like of our inverter design. Like PMOS is the parameters for this PMOS are K bar P is equal to like 60 microampere per volt square. Then we have VTP, which is equal to minus 0.7 volts. Then we have CJ here, which is equal to 1.05 femtofarad per micrometer square. And then we have CJSW, which is equal to 0.32 femtofarad per micrometer. So we have these parameters, like all these parameters are for our PMOS. Then we have few parameters for our NMOS, which are like we have K bar N, this is equal to like 150 microampere per volt square. We have VTN, this is equal to 0.6 volts. Then we have like Cj, this is equal to 0.86 femtofarad per micrometer square. And then we have like CJSW, which is equal to 0.24 femtofarad per micrometer. So we have these quantities for our NMOS, and these are like these quantities are for our PMOS. So what we do is like there are different other parameters which are linked with our design. Here we have like L is equal to 1 micrometer. Then we have L0, which is equal to like 0.1 micrometer. This one is our drawn length. And then we have this VDD, which is equal to 5 volts. And we have our like C oxide capacitance, which is equal to 2.7 femtofarad per micrometer square. So we have all these parameters for our MOSFETs. So using these parameters, we can design an inverter that we can find the capacitances which are linked with these inverters. So for that we have to solve different parameters. We have initially we have we have to find like input capacitance, we have to find CMOS capacitance, and then we have to find output capacitance. What that means is we have to find different capacitances that are linked with our inverter design. Like we have this inverter here, this is our VDD, this is our ground, we have the in here and we have the out here. And if we highlight some of the capacitances present here, we have a few capacitances which are linked with this input area. These are known as our input capacitances. Then we have a few capacitances which are linked here. We have studied that earlier. We have different drain and source capacitances. So these are our MOS capacitances, and we have a few capacitances which may appear here at this terminal. So these will be our output capacitances. So we have to find one by one what these capacitances are, and how can we find how can we calculate all these values. So first what we do is at first we have to find the input capacitance, like this capacitance here. So the input capacitance can be given by CG this is given by CGP plus CGN, like the gate capacitances of our PMOS and gate capacitances of our NMOS. And we know that this CGP is given by this formula is C oxide L and WP. We know that CGP is equal to C oxide L WP. We have all these quantities present here. We have oxide here, and then we have lengths also defined by our parameters, and then we have WP. If we put all the values here, the values are 2.7 into 10 power minus 15, and then we have L is equal to 1 micrometer, that is 10 power minus 6, and then we have our like WP, that is equal to 8 into 10 power minus 6. This quantity is for our PMOS, so we are only talking about our PMOS design. So this is our CGP, and for NMOS we have CGN, which is equal to like C oxide L and WN. So we have to put the same values here, 10 power minus 15 and 1 into 10 power minus 6, and now like this Wn is equal to 4 into 10 power minus 6. So the difference comes here. So the CGN will be equal to value for this CGN will be equal to 10.8 femtofarad. And if we have to find the overall like input capacitance, like overall input capacitance, that is given by Cin CGP plus CGN. So these values turn out to be like these values are 21.6 femtofarad plus 10.8 femtofarad. So total Cin capacitance is 32.4 femtofarad. So this is our total capacitance that can be used for our like the inverter design. And then we can say that like if we just highlight it here, this is our total input capacitance. Now what we have to do is we have to find the like CMOS capacitance, like the capacitance that appears on our MOSFETs. For that, what we have to do, we have to like what we have to do is like CMOS capacitance, the like C of MOSFET can be calculated by this formula which we have studied in this session earlier. This is equal to CDN plus CDP. Here this CDN value, like we have to solve this separately, like CDN and CDP separately. First we solve this for like this PMOS here. For PMOS junction capacitance, we have this formula like CDP is equal to 1 by 2 this VG like VGP plus CP, and we know the value here which is CGP, but we have to find this value like this. We have to solve this value for like CP. This CP is given by like C of J, we write it here P, and then we have like area of P, like area of bottom P, CJSW, and then we have perimeter of this P. parameter for this PMOS. Here AP is given by X plus L naught and WP, and like why we are using here X plus L naught, because we have drawn it something like this. This was our gate terminal, this was our NMOS. We said earlier that this length is R2, and we have some overlapping here, which basically represents our L0. This value 2 and L0 should be added together, because our total N plus region or P plus region, our total P plus region is from here to this point. It's not from here to this point. So our total P plus region would be X plus L0. So we are calculating it using this formula. Then if we put the values together, 2 micrometer plus 0.1 micrometer, and if we multiply this with 8 micrometer, this comes out to be 16.8 micrometer square. This area is for our AP, for our PMOS. Then we have to find this parameter value, that is PP. This is equal to 2 into X plus L0. This X is now with capital, X plus L0, and then plus we have to add it WP here. If we put the values in this expression, we have 2 micrometer plus 0.1 micrometer, and then we have 8 micrometer. So this P of P is equal to 20.2 micrometer. Now what we have to do is we have to put all these values in our expression for CP. We have CP, and then we have to put all these values here. First we have to put the value of CJ, 0.5 femtofarad per micrometer square. This is multiplied by 16 this is multiplied by AP, 16.8 micrometer square, and then we have to add a term which is CJSW, 0.32 femtofarad per micrometer square, and then we have to multiply this quantity with perimeter of PMOS, that is 20.2 micrometer. So our CP comes out to be, the final value of CP is 24.10 femtofarad. Now we have to find the drain junction capacitance. This capacitance is 21.6 femtofarad divided by 2 plus 24.10 femtofarad. This expression here, this represents BGP, and this represents what we calculated here, this represents CP. So the final value for our drain MOSFET drain capacitance, it will be equal to CDP will be equal to 34.9 femtofarad. So this is our final expression for CDP. Now we have to find the same values for our NMOS, like NMOS junction capacitance. So for NMOS junction capacitance, we have similar formula, that is CDN is equal to 1 by 2 CGN plus C of N, and this C of N is given by C of N is equal to Cj A of N plus CjSW A of this is our P of N. If I correct it here, this is our P of N. We know the value of, we can solve this value for A of N using the same formula. A of N is equal to X plus L naught, and we have to multiply it with Wn. So if we put the values, which are 2 micrometer plus 0.1 micrometer, and we multiply it with the width of NMOS, that is 4 micrometer, the final expression would be, the final value of A of N will be 8.4 micrometer square. So if you observe it here, we have designed this inverter something like this. We had this as an PMOS, and we had this as our NMOS. We observed here, at this point, the points these points here, the X value, this is same for this NMOS as well. This is 2 micrometer and this is also 2 micrometer, and similarly this L naught overlapping here, the L naught overlapping is also same for our NMOS and PMOS. So we are using the same values here for our X plus L naught calculations. Then we have to find the parameter of our NMOS. So the parameter formula would be P of N is equal to 2 into X plus L naught, that is N plus W of N. So if we put the values here, this is 2 into, if we sum these together, these two will be 2.1 micrometer, and plus we have W naught is equal to 4 micrometer. If you solve this expression, the parameter P of N would be equal to 12.2 micrometer. So what we can do here is, we can now solve the expression for C of N. If we put the values back in for C of N, first we have to write the value of Cj for NMOS, that was equal to 86 femtofarad per micrometer square. This is multiplied by our A of N, that was equal to 8.4 micrometer square, and then we have to add another quantity, that is CjSW for NMOS, which was equal to 2.24 femtofarad per micrometer square, and we have to multiply it with the parameter of NMOS, which was equal to, which we found to be 12.2 meter square. So if we solve this Cn, that comes out to be 10.15 femtofarad. And now if we have to find the total capacitance, total NMOS capacitance, obviously that is junction capacitance, this will be equal to CDN, which is equal to 1 by 2 CGN n plus C of n. We know the value of CGN that we calculated earlier, that was equal to 10.8 femtofarad divided by 2, and then we have to put the value for Cn that we calculated it here. This is equal to 10.15 femtofarad. So if we solve this expression, that CDN value comes out to be like 15 femtofarad. So we can say that the total capacitance would be the sum of like PMOS junction capacitance and NMOS junction capacitance. So the CMOS capacitance will be equal to CDP plus CDN. If we put the values here, like this CDP was 34.9 femtofarad, and this CDN was that we calculated just now, 15.55 femtofarad. So the total value CMOS is equal to 50.45 femtofarad. This is our like second expression which we have to find, which we were looking at, like our CMOS capacitance. So the third quantity, is our C out, and we can like define it as C out is our CMOS and plus our like load capacitance. So we can say that this load capacitance CL is load capacitance, or this can be input capacitance, which is attached at output of inverter. So like this CL could be the input capacitance of a load that is connected to the output of our inverter. So we can say that this C out will be equal to 50.45 femtofarad plus CL. So this is our total output for our like design. This is our output capacitance. So we have found that we can solve, or we can find the input capacitance of our of our inverter. Then we can find the MOSFET capacitances, like the capacitance of our inductor, the inverter, and then finally we can find the capacitance of our output, like output capacitance of our inverter. So this was it for this example session. I will like leave you with a simple question here. That question is related to understanding of what is the output capacitance and of an inverter. So the question is like, what is the
what is the output capacitance, like this C out here. What is the output capacitance if the inverter is driving a similar inverter? Like, we are talking about a condition where we have one inverter and this inverter is driving another inverter that is a similar inverter to this, like this inverter. So we have to understand like what will be the output capacitance of this inverter, like this total output capacitance of, what will be the total output capacitance of this first inverter. Obviously that can be found from this formula here. So that is a question for you to understand. So think about it, and you can post me questions or comments. So this is it for this session. We will have another session where we will study how we can control the rise time and fall time of an inverter or for our logic gates. So this is it for today, and I will see you in next video, inshallah.